Hello everyone, this is Dr. Webb. Welcome to this calculus video where we will be talking about maximums and minimums. So what is a relative maximum? So relative, sometimes called a local maximum, occurs at some point f of a if around that x value a, f of a is at least as big as all the other function values. So f of a is greater than or equal to f of x for all other x in some interval centered at a. And a minimum is just sort of the opposite of that. So a relative or local minimum occurs at bf of b if f of x is greater than or equal to f of b for all x in some interval centered at b. At a relative maximum or minimum, f of x can be neither increasing nor decreasing. Because let's suppose that we're at a relative maximum, and if we're at a relative max and f of x was increasing there, well, then that means that if you went to a little bit to the right of x, the function values would be higher. So if you had some point and the slope was increasing, so it was going up, well, if you moved a little bit to the left, you get function values that were higher, and that can't happen. Same thing, it can't be decreasing there, because if it's decreasing, rather than going to the left, rather than going to the right, we could go to the left a little bit, and we would get function values that were bigger than before. So f of x can't be either increasing or decreasing there. Same thing is kind of true for a minimum. If it was a minimum and the function was increasing there, then that means if you moved a little bit to the left, you'd be lower. If it was decreasing there, you could move to a little bit to the right and be lower, and that would mean that it wasn't a relative minimum. And so if it's neither increasing or decreasing, that means that either the derivative there has to equal 0 or it doesn't exist. The derivative can't be positive or negative because then it would be increasing or decreasing. Okay, and so these are sort of the possibilities. So here you have a relative min first, and so you can see right here the slope is 0. Here we have a relative max at the top, and right here at the top you see the slope of this. The tangent line to this is horizontal. And then here we have what's called a cusp, and so these 2 points are coming up to create a maximum min, and there's no derivative at that point. There's no one tangent line. There's 2 separate lines coming in from the left and the right, and so this is an example of a relative max where the derivative of the function doesn't exist. So let's give a little bit more of a formal argument as to why the value of a derivative has to be 0 at, in this case, let's focus on a relative max. So let's suppose that f of a is greater than or equal to f of x for all x values near a. So we're talking about a relative max here. So this is telling us we're dealing with a max because f of a is bigger. And also we're going to suppose that f of x is differentiable at a. Well, if it's differentiable at a, then we can calculate the derivative using the limit definition. And so we have this limit as x goes to a of f of x minus f of a divided by x minus a. This exists. And so if this limit exists, this means that the 2 one-sided limits exist. So first let's focus on the limit to the right. And so this limit on the right exists, and it's still going to equal the derivative. And so then on top we have f of x minus f of a, but we know that f of a is greater than or equal to f of x for all x values near a. And so that means that f of x minus f of a, f of x, this is smaller. And so we have f of x minus f of a, which is bigger than it. So the top here has to be negative. But the bottom, or at least non-positive, so let's not say, it could be 0. You could have values of f of x that are equal to f of a there, and that's perfectly fine. So we can say that the top here is less than or equal to 0. On the other hand, if we're taking the limit from the right, so the x values are bigger than a, x minus a, this is going to be strictly bigger than 0. So we have something on the top that's less than or equal to 0, something on the bottom that's strictly bigger than 0. So we have something like a negative number divided by a positive number, and so this has to be, overall, less than or equal to 0. something negative divided by something positive. So we know that tying this back to the value of the derivative, we would know that the derivative has to be less than or equal to 0 by looking at the right side. However, when we look at the left side, the value of this limit still has to equal the value of the derivative. And f of x minus f of a, this still has to be less than or equal to 0. But now the bottom, x minus a, since x is to the left of a, x is smaller than a. And so now the bottom has to be negative as well. And so we have a negative number divided by a negative number. And so in this case, this is saying that the value of the derivative has to be at least 0. So it has to be greater than or equal to 0. And so putting these two together, the value of the derivative would have to be both less than or equal to 0 and greater than or equal to 0. Well, the only value that that's true for, so the only value such that you could have the derivative be both greater than or equal to 0 and less than or equal to 0 is if the value of the derivative actually is 0. 0 is the only number that's both greater than or equal to it and less than or equal to it. Okay, so here's a graph of a function. We've got a couple relative maxes or mins going on, and we can see we have a relative min going on at this point, and you can see the value of the derivative here is 0 because the tangent line is horizontal. We have another point right here, that's a relative max where the derivative is equal to 0, and then we have this relative minimum right here where the derivative is equal to 0. So all of these, in this case, for these relative maxes or mins, in all of these, the value of the derivative exists, and they're all equal to 0. Okay, so if we're trying to find relative maxes or mins, we're looking for places where the derivative is equal to 0. And so we're going to call those places critical points. So the critical point of a function is a place where either the value of the derivative equals 0 or doesn't exist. So the maximum minima, from what we saw before, these have to occur at critical points. But just because something is a critical point doesn't mean that it's a maximum or minimum. So if you look at this point right here, this looks something probably like a cubic. At that point right in the middle, the slope is horizontal, but it is neither a max or a min. It can't be a max because points to the right are higher than it. It can't be a min because points to the left are lower than it. So this is neither a max or a min, but the value of the derivative in the middle there is 0, so it is a critical point. So being a critical point doesn't guarantee that you are a relative maximum or minimum, but if you are a relative maximum or minimum, you must occur at a critical point. So here is a cubic right here, and let's try and find the critical points for this. So first, let's calculate f prime of x. And since this is a polynomial, that's not going to be too bad. Minus x cubed goes to minus 3x squared, plus 3x squared goes to 6x, plus 9x gives me plus 9, and then the minus 4 goes to 0. So the value of the derivative is minus 3x squared plus 6x plus 9. So this is a quadratic now. So this exists everywhere. So there aren't going to be any critical points where the derivative doesn't exist. But we can find the critical points then by setting this equal to 0. And so we have 0 is equal to minus 3x squared plus 6x plus 9. I can divide everything here by minus 3 and get x squared minus 2x minus 3. And then this factors nicely. I believe this is going to be x minus 1 and x minus 3, or actually x plus 1 and x minus 3. Yeah, 1 times minus 3 gives me minus 3, minus 3 plus 1 gives me minus 2. Good. And so this means that our x values for our critical points are at minus 1 and 3. So these are the two x values where the critical points lie. Okay, so now that we have the critical points, How do we tell whether it's a relative maximum or minimum? Well, if it's a relative maximum, if you look at this, to the left, the function is increasing, and then to the right of the point, the function is decreasing. And so over here, we have f prime of x is positive. Over here, we have f prime of x is negative. And so at the critical point, the derivative of the function has changed from being positive to negative. So at a relative maximum, the function is changing from increasing to decreasing. What about a relative minimum? So same idea. To the left of the point, the function is decreasing. To the right of the point, the function is increasing. And so the derivative of the function is going from negative, decreasing, to positive, increasing. And this corresponds with the curve being concave up. So if it's a maximum, the derivative is going from positive to negative, and its curve is concave down. If it's a minimum, the curve is changing, the derivative is changing from negative to positive, and the curve is concave up. So let's go back to this cubic we were looking at before. We saw before that our critical values were at -1 and 3, and the value of our derivative was minus 3x squared plus 6x plus 9. And so if we're trying to figure out whether or not this is what's happening at each of these critical points at 1 and 3, well, to figure out what's happening between -1 and 3, I can plug in, say, 0. If I plug 0 in here, I get 9 out of my derivative. And so the derivative values are positive between -1 and -3. If I plug in something a little bit to the left of -1, so say -2, this would be -3 times 4 is -12, minus another 12, plus 9, that is going to be less than 0. So I am negative over here. Same thing if I plug in a point to the little bit to the right of 3. So if I plug in 4, I'm going to have -3 times 16 is -48, plus 24 plus 9. So that's -48 plus 33. That is also negative. So my function is going down as I come into -1, and then up coming out of it. So it's going from negative to positive. So that means at -1, we have a relative minimum. At 3, the function is going up and then going down to the left of it. So it's changing from positive to negative, increasing to decreasing at 3. And so if the function's changing from increasing to decreasing at 3, then we're thinking about a relative maximum. Okay. And that is all for this video. I will see you again soon.